relativity, truck pools, and laser-sighted orange cannons. That's what's up next on PS 100. Before we dive in, let's cover some basic vocabulary. First, we have the principle of motion symmetry, which says everything within a reference frame seems stationary as long as that reference frame's motion remains uniform. If you've ever tried to eat a steaming hot bowl of soup while driving, you've seen this in action. Things appear motionless as long as you don't speed up or slow down. The same principles are at work when you're riding in a truck pool. Because the truck isn't accelerating in any direction, we consider it an inertial reference frame. But as soon as we accelerate in any direction, the truck becomes a non-inertial reference frame, and everything begins to slosh around. So you don't notice the motion of inertial reference frames because they are in uniform motion, and you do feel the motion of non-inertial reference frames because they are in accelerated motion. This is pretty basic stuff, but motion symmetry gets interesting when you put things in motion from an inertial reference frame. Let's say we're shooting oranges at space signs while flying through space at 60,000 kilometers per hour. Since we're not accelerating, it feels like we're motionless, and to us, those oranges are only going about 100 kilometers per hour. But from the sign's reference frame, those oranges are flying much faster. The speed of the orange gets added to the speed of the truck, and the orange blasts right through the sign. Motion symmetry gets even more interesting when your reference frame is moving close to the speed of light. Let's say we're going 3/4 the speed of light while we're shooting out our oranges. From our reference frame, it'll still appear that the oranges are flying at 100 kilometers per hour. Now, it seems like we should just add the truck's velocity and the orange's velocity together to figure out how fast they're going from the sign's reference frame, right? Nope. Things get weird when you get close to the speed of light, so you have to use a special equation to calculate relativistic velocity. But you don't need any fancy math to calculate the velocity of the laser light when it's shot from our space truck. The special theory of relativity says that light always travels at 300,000 kilometers per second, no matter how fast the light source is moving. So if we measure the speed of the laser's light from the truck's reference frame and from the sign's reference frame, both measurements would come out to 300,000 kilometers per second. That doesn't seem to add up, but that's just what light does. It's a constant. It may sound like motion symmetry doesn't apply to light, but in his special theory of relativity, Einstein says it does. In fact, Einstein's special theory of relativity is based on these two principles. Motion symmetry applies in all inertial reference frames, and light always travels at 300,000 kilometers per second in a vacuum, no matter what your reference frame is. The crazy thing is, if motion symmetry applies in all inertial reference frames, the only way the speed of light can be a constant is if space and time are not. As it turns out, when you travel at extremely high speeds, your length gets shorter and time slows down from an observer's reference frame. Which is weird. Oh, and your mass increases. Of course, you still wouldn't be able to tell from within your reference frame. And since you'd feel as if you were standing still, anyone you passed by would look like they were the ones flying near the speed of light. So their length would appear to be shortened and their time would seem slow. That's it for this episode, but you'll find more science and research opportunities for BYU undergrads in the description below.